All right, if you've ever worked with an ARM CPU, you've definitely heard of exception levels. But what are they really? It's one of those core concepts that can trip up even the most experienced developers. So let's spend the next few minutes clearing up one of the biggest, most common points of confusion in CPU architecture once and for all.
Yeah, this quote, it just hits the nail on the head, doesn't it? It perfectly captures that feeling. So if you've ever felt a little fuzzy on this topic, trust me, you're in very good company. Let's untangle this whole thing together right now.
So this is the picture that pops into a lot of people's heads, right? The idea that inside a single CPU core, there are these, I don't know, separate little hardware blocks, like one section for user mode, another walled-off area for the kernel, that kind of thing. It feels logical, it makes a certain kind of sense, but is it actually right?
Nope. A big, fat, unambiguous no. And honestly, if you take away only one thing from this, let it be this. Privilege levels are not physical divisions inside the chip. So, okay, if that mental model is totally wrong, what's the right way to think about it?
Okay, so the whole confusion really comes down to mixing up two different things, the physical hardware itself and the state that hardware is in at any given moment. We got to separate the what the thing is from what the thing is allowed to do right now. And this is the absolute key. A single ARM core is, well, it's a single unified piece of hardware. There are no separate sections for different privilege levels. Instead, the entire core just operates in different modes. It's kind of like how your car has park, drive, and reverse. It's all the same engine, same transmission, but it behaves completely differently depending on which mode you've put it in.
All right, so let's zoom in on just one of these cores. If there aren't these separate hardware blocks, then where's the magic happening? What's the control center that's actually telling the core which mode it's supposed to be in? So this definition right here is super important. A privilege level is simply an execution state. It sets the rules of the road for the CPU at any given moment. And check out that last part, it's critical. The core is always in exactly one level at a time. It's not splitting itself, it's not multitasking its personality, it just switches its entire state.
And here it is, the answer. The control center isn't some big, separate chunk of silicone. It's actually a set of really small but incredibly powerful special registers located right inside the core. These are the real gatekeepers. So what do these special registers actually do? Well, you can think of them as holding the configuration that defines the core's entire reality. They answer questions like, what privilege level am I in right now? What parts of memory can I touch? What instructions am I even allowed to execute? And the amazing part is, just flipping a few bits in these registers completely transforms the behavior of the entire core. Okay, so theory is one thing, but let's make this real. Let's trace one of the most common things that happens in any modern OS, a system call. We're going to see how this mode switch actually works in the wild.
Okay, let's follow the journey. Imagine your web browser is running. It's chugging along in the least privileged mode, which we call EL0. Now, it needs to open a file from your hard drive, but it doesn't have the permission to do that directly. So what does it do? It executes a special instruction, SVC. Think of this as pulling a help cord. The hardware sees this, and instantly, automatically, it saves the browser's current state, flips that current EL register from EL0 to EL1, and hands control over to the operating system kernel. It's this super fast, seamless, hardware-managed transition into a much more powerful mode. And this table just lays it out perfectly. Look what changes. The privilege level switches from user to kernel. The task switches from running your app to running the OS. But what's the one thing that stays the same? The core. It is the exact same piece of hardware, same pipeline, same everything. It's just operating under a new set of rules. Okay, cool. That makes sense for a single core, but, our phones and laptops have tons of cores these days. So how does this whole idea scale up across a multi-core chip?
Here's the next big rule you need to remember. Each CPU core is completely independent. When it comes to privilege levels, every single core is its own island. There's no central boss, no shared manager. Each core is the master of its own state. So check this out. This is like a snapshot, a single moment in time on a 4-core CPU. And just look at what's going on. Core 0 is just running a user app, totally normal. But Core 1 is in kernel mode, probably handling some hardware interrupt. Core 2 is off running a totally different app, also in user mode. And then you have Core 3, which is running in hypervisor mode, managing a whole virtual machine. They are all in different states, doing completely different jobs, all at the exact same time. And how is this chaos possible? Well, it's because each core has its very own set of those critical system registers we talked about, its own current EL register, its own state. They don't check in with each other. They just manage their own state changes based on the work they need to do. All right, we've gone through the technical stuff, but to really make this new mental model stick for good, let's use a really simple analogy. I want you to imagine that a single CPU core is an expert engineer. Super smart, super capable, can pretty much handle any task you give them. Okay, now here's the key part of the analogy. The privilege levels, they aren't different engineers. They're just different security badges that our one engineer can wear. And each badge, of course, gives the engineer different permissions. So the user badge, that's EL0, lets them access the standard office areas, their desk. But if they need to get into the server room, they have to swap it out for the admin badge, that's EL1. The hypervisor badge, for EL2, that gets them into the entire data center. And the secure badge, EL3, well, that's how they open the company vault. This really sums it up perfectly. It's the same person. The engineer's skills and knowledge haven't changed at all, but depending on the badge they're wearing, they can open certain doors. That is exactly what a CPU core is doing when it switches privilege levels. And to bring it all home, a multi-core CPU is just like having 4 of these engineers working in the same building at the same time. At any given moment, one might be in the server room wearing their admin badge, while another is at their desk with their user badge. They're all independent, each with their own badge, doing their own thing. So let me ask you, the next time you think about CPU architecture, what are you going to see? Are you going to picture those separate, walled-off blocks of hardware? Or are you going to see one really smart engineer just quickly switching their security badge? Because once you replace that old, confusing model with this new one, you've really unlocked the right way to see one of the most fundamental concepts in all of computing. It's not about being in different rooms. It's all about which badge you're wearing.